you've probably seen things like in painting where you can edit a diffusion image, and this is basically a way to kind of formalize that and do it. Is paper was made in 2022, and it basically shows a method, and it's kind of what you would expect to in-paint and kind of edit an image. As the name suggests, it's SDEdit. So what they propose is they propose a method using an SDE to solve, to basically edit an image, whether that's in-painting or whether that's doing image-to-image, like full image-to-image translation, or some other thing, forget what they call it, composting, image composting. So they kind of have three things they show off, but the reason I'm kind of going over this now is because I also want to go over the Stable Diffusion XL paper, and this paper in particular is used by Stable Diffusion XL. They cite SDEdit just so that they can get another model. This is particularly the refinement model. They use an SDEdit model to do the refinement task. If you've already read Stable Diffusion XL. So, anyways, yeah, we'll start with diffusion and go through the rest. So, first off, what is the goal? So, the goal is just kind of three things. Two in a way. So they kind of formalize, they kind of say that the goal is, given this garbage drawing of a scene, maybe you got some mountains in the background or something. Beautiful. That is a scene right there. So this was drawn by me, and kind of the goal is to turn this into a good-looking image. So you actually would have some nice, I'm not even going to pretend to draw some nice-looking backgrounds, but if we go here, it'd probably be better to show off, because I can't draw a nice scene. But you have this initial scene here. This is your, what they call a guide. And what you want to output is something that looks similar to this image, but something that also looks good. So they kind of call this the faithfulness trade-off, or the faithfulness realism trade-off. So this image is very realistic, but you also want it to be faithful to the initial sketch that the human drew. But they also have this composting task, which is kind of like here you would put some glasses on an image, like you would or I guess not Photoshop them on, just throw them on the image, and then you can see. So this is our original image. We throw some glasses on there, it looks bad, and then it diffuses it into something that actually looks good. Same here, but with the hair. So you can see we got the hair, and then you Photoshop some different hair on, and then it diffuses it into an actual good-looking image. And that's kind of the second thing they do. And the third thing they do is stroke-based editing, where you take your original scene. This is your in-painting. You take your original scene, and you're like, I want a field here, so I'm going to draw kind of this field-looking thing here. And, well, I guess it generated trees in this case, so maybe you want some trees here, and it generates trees. But that's the faithfulness realism trade-off, because if I wanted a field, then I guess it didn't particularly do that, but yeah, that's the goal. Basically, you're giving it an image and you're editing it in some way, and then you want it to actually look good. So it's and Stable Diffusion XL doesn't use it in this way. They use it in a different way, but it's the same idea. So that's the goal, and it's very powerful if you can get something working that actually does this. There are other methods that they describe. So there's these GAN methods. There's kind of two of them. There's two GAN methods. One is image to image. So maybe I have these latents. These are our latents, and then I throw it through our generator in the GAN, and then I get our image. So maybe this is the garbage-looking scene I drew. And maybe it's probably a lot better than that, but maybe it has some artifacts in there from how this GAN produced the image. And maybe you get another GAN that maybe increases the resolution, or maybe perhaps makes it look a bit better. So maybe you have a second generator. that makes it a little bit better. Maybe it'll also increase the resolution, so you actually have a good looking scene if this was good looking compared to this. But you probably get the idea. You basically have a second generator. Now, the downside to doing this is for each, they describe for each new editing task, it requires separate data collection and retraining. So you have to, it's a very expensive process. You have to retrain this module, and it's not very, like, it's not a very easy method to do. Now, a second method is, say I got this image of a scene. So this image of the scene, I keep drawing, and then so this was produced by your generator. Actually, let me just take this image. So you have this image of a scene produced by the generator, and maybe I go back and I do some sort of reverse process where I get the predicted latents, so maybe L hat, and I kind of edit the latents very slightly. So I figure out kind of how to edit these latents to make the image look more like the style I want it to look at, and then you read. So I'll edit these, edit. Maybe I get latents L bar, and then I throw them through the same generator. So it would be this would be the same generator, but drawing it down here, and then this would generate the image maybe with a little bit better quality, or maybe you wanted to add maybe a lake over here or something like that. But you basically edit the latents in a way such that the output image corresponds to your desired goal, whatever that may be. But you can kind of think that this is going to be very difficult to do. Like, since we don't really know what the latents represent, and it may be an entangled latent space, and this probably isn't going to work out very well. And also, if you do the reverse process, the latents are probably an estimate, so it's not going to be perfect, and the GAN inversion isn't probably going to be too good of a technique. Now, there really aren't. I think at this time there weren't a lot of. I don't think there were any diffusion. So when was this made? Yeah, I don't think there were really any big diffusion models at this time, which is kind of weird, because it doesn't seem that long ago since, or it wasn't that long ago since diffusion models kind of blew up. But there weren't any like good editing diffusion models, unlike today where you can edit an image really well. But it uses this method, like the stable diffusion, image to image. It uses this method, the inpainting and stuff. So first off, let's just start with what is a diffusion model. So a diffusion model, the general diffusion model is, say we got this image of a cat. So we got our cat there, beautiful. Nope, not drawing the nose. we got our cat there. Yeah, okay. Yeah, it looks terrible. We got our picture of a cat. Now, this is what we will call, say, x sub 0. So this is our x0. I think that's how they describe it. Yes, x0. Just want to make sure I get the subscripts right. Yeah. So this is x0. This is our original input image, and this is the image we basically want to teach a model to produce, except it's a bigger distribution. But what you do is you take this image and you kind of add a little bit of noise to it. So you take this image. Let me redraw this. Okay, well, it's even worse now. But yeah, you add a little bit of noise. So let's just say looks like this now. So there's a little bit of noise here, and then you do this again. So you'd take the same image and you add a little bit more noise to it. So we make it a little bit more noisy, and you keep on adding more and more noise to it. So this would be, say, x sub 1, this would be x sub 2, and you keep doing this until you get a full, so you do this over and over again until you get a full noisy image, which is pure Gaussian noise. So maybe that'll be red. So you have this pure Gaussian noise image. So you take your original image, you add a little bit of noise to it, and you keep doing this over and over again until you do this theoretically to infinity, but you can kind of you only need to do this to like 1,000 steps or so to add noise to this image for like 1,000 steps, and then you get out your your Gaussian noise image. Now what you do is you train a model to reverse this process. So you train a model, say p theta, to reverse this process. So it takes the image at time t, so it'd be x sub t, and it takes in the time step t, so it kind of knows where it's at in this process, to remove the noise. And you do this for all steps, and it's the same model. So this would be p theta of x sub t given t, and p theta of x sub t given x sub t and t. And you basically train a model to learn how to denoise an image at every point in this time step. So then what you can do is you can give it this noise, and it can generate an image. It can generate whatever image corresponds to that Gaussian noise, whatever it generates. Whether this is a deterministic process or non-deterministic process, it doesn't really matter either way. If you're it'll generate an image from noise, and you theoretically have unlimited images that you can generate. And if you also want to add text, you can add text during this process. Maybe the text is a picture of actually we'll make it this a bad picture of a cat. There we go. So maybe this is our text, and maybe we throw our text through some sort of encoder. It gives us some embeddings. Maybe this is a vector, and then we just throw this through the model at each time step. And that's how you would kind of condition it on text. And you can condition it on other stuff like Stable Diffusion does, but this is basically all you're doing. You're just teaching a model to take an image with noise in it and to remove the noise in the model, or to remove the noise in the image. Now, the way you do this is with a formula. Maybe it looks something like this. Maybe you have a scheduler, alpha t. This is x sub t, this would be x0 plus square root of alpha t, 1 minus alpha t. So maybe alpha t is your noise scheduler, maybe that's linear, something like that, and it basically tells you how much noise you have in your image at any time step t. And this is kind of the formula you usually see for the diffusion process. You basically have this scheduler that's strictly decreasing. So at time step 0, you would initially have, say, alpha t is equal to 1, and then or say alpha 0 is equal to 1, and then alpha t, big T, where big T is your maximum number of time steps, maybe that's 1,000, is equal to 0. So at time step 1, or at the initial time step, you basically have this image, and then at the last time step, you have all noise. And this allows you to jump anywhere in the diffusion process. So you can give it any time step, and you can basically jump anywhere in this diffusion process within one step, as opposed to noising it a bunch of steps over and over again. So this formula allows you to jump anywhere, and you just sample from this Gaussian distribution. And because Gaussian distributions are so nice, you have this variance here, which basically controls the variance in the Gaussian. And as you go further in the diffusing process, the variance increases in the Gaussian, or from the Gaussian you sample. So it's a very nice property. You can just skip immediately to a time step in the diffusing process. Now, you basically train a model to minimize this loss. So you have this loss here, which is, so we set z here. So z is our noise in our image. So you have z minus z hat, where z hat is your predicted noise and z is your actual noise. So you basically take an image, so for example, you take this image of our cat and you noise it to a certain time step in here, and then you train a model to reverse the process by one step. But a better way to do that is to say, what is all the noise in this image? So you basically give it an image at anywhere in this step, and it's like, oh, I think all the noise in this image, it basically predicts all the blue in this image here. So then you can basically skip all the way back to the beginning of the process, and then you basically say, okay, that was a good first prediction maybe, and then you move one step back in the process. So you basically do this alternating between, so you like start late in the process, you have it predict all the noise in the image, and it's not going to be a perfect prediction, so then you move back in the process a little bit, and then you have it predict all the noise one step less in your process, so it'd move back here, and then you add a little bit more noise, and so on. So you keep on alternating between this, and the way you do this is by having the model predict all the noise in the image. So this way you can kind of skip steps in your diffusing process, and that's how you can speed up diffusion. But yeah, this is the goal they have. And more specifically, z hat would be our model theta, which is given x sub t and t, where x sub t is this thing up here. And you can see basically it has to remove this part here from from x sub t, and then it would just have the noise in the image. So this would be our mean squared error loss, and that's all you're doing. You're just having it predict noise, and then you can do this diffusing process. Now, that's cool and all, but this actually is no longer really used in practice, actually. What is used in practice are SDEs and ODEs. So it's a very similar thing, and actually SDEs, the SDE formalization of this process was created before the diffusing process. So before the DDPM paper came out, there was this SDE. There were many SDE papers, which are called score models, and they were proposed by. I don't know exactly who they were proposed by, but I know that Song. I don't know his first name, but Dr. Song kind of did a lot of work in this field, and he kind of made him, at least from what I've seen, he kind of made it really big, the score models, and then that transformed to kind of what you see today. But like while you had GANs kind of going on, Dr. Song was kind of working on these models, and it's kind of cool to see. But anyways, the formalization is, you can kind of see it's similar. Yeah. So this is a formalization, and yeah, this is a formalization for the forward process. So basically, you have this. I mean, this looks very similar, but you have this first term here, which is your data term, and then you have this second term here, which is your noise term, and you can actually model this as an SDE. So yeah, you can see they say we suppose that x sub 0 is the initial data sampled from your data distribution, which represents a sample from the distribution in a forward SDE that produces x sub t for all t via Gaussian diffusion. So the forward process is the same as your diffusion. You can also make this a little bit different. I think the initial paper did the initial like SDE paper, a diffusion or score-based model paper actually made this a differential here instead of this diffusion model formulation, but it doesn't really matter. Basically, the forward process is kind of the same. Now, the reverse process is different. You're not predicting noise, rather you're predicting what's called score. So score is different. Score is this thing right here. So if you break this down, you have your data x. P sub t is your data distribution at time t to your PDF, and you basically have the log of your PDF. So you have the log of your data distribution, and you take the gradient with respect to x. So you can kind of think of this as like we have our data distribution here, and you can think of the score as kind of pointing in the direction of high density areas in your data distribution. So maybe you have a really small gradient here, really large gradient here. But yeah, you can think of this as this gradient field where the gradients are pointing in the direction of high density parts of your data distribution. And maybe you have, let's say we have our data distribution, and it's CFAR 10. So actually, let's make it simpler. Maybe you have do the good old example. You have a data distribution of cats. So maybe this is your good-looking cat. Well, as good-looking as I can draw. So this is very high density. You want an image that looks like this. And maybe you have a similar distribution here. Maybe it's a picture of the a full cat as opposed to just a face. But those are images you want. And then at these low density areas, maybe you have a picture of, I don't know, maybe you have a picture of a chair or something. Maybe you have a chair in that in your data for some reason. So maybe this is a picture of a chair. Maybe this is like really smudged picture of a cat, something like that. So you don't want those. You don't want those pictures. You want the high density. You want the high density areas. So your score is basically telling you what direction you want to move. So like kind of where you at and what direction you want to move to get to a good looking an image you want, a good looking image according to the data distribution. So it's very different formalization than the diffusion formalization. You're modeling the score, not the noise in the image. But you can, like, this is a generalization, so you can make this model noise, and that's why they use SDEs. So the reverse process basically says if we can have a model predict the score, so that's this part here, then we can reverse the process according to this differential here. Now this differential is kind of hard to look at. I think it's easier to look at the. Okay, I'm gonna butcher this name because I don't know how to say it. Euler, so Maruyama. Euler-Maruyama, whatever, that method. This method is basically a solver for SDEs, so it allows you to solve this method numerically. And if you've seen the Euler solver method, it's basically that, but it's basically the simplest method you can have for an SDE. And I feel like this is pretty intuitive, the method here. So you basically have three parts. The first part, so your next step, so assuming we have, say, an image in this low density region, and we want to move to a higher density region, then to move in this higher density region, you basically say, okay, we have our image at time step t kind of -1 in a way. So this is basically t -1. This is your previous steps. This is where are we currently at. Yeah, update rule from this to t. So this is your, like, the reason they have plus delta t is because this is technically in the future. So this would be a step here, which would be, say, t is equal to like 1000, and you want to move to step 999. But yeah, this is your previous step. Previous in quotes, because it's the step you want to move away from. You want to move away from this step to this step to go to the higher density region. So this is your previous step, your quote more noisy step, and what you want to do is basically step in the direction of the score. So that would be, so we have this first term. The second term is stepping in the direction of the score. So you have sigma theta t plus or minus sigma theta t plus delta t. And then you have your score, s theta. So this part here is basically like how much, or like the difference, like it's a change in your variance from the previous step to the current step. And you update your score based on that variance. And then you add a little bit of noise to here. So plus sigma theta t minus sigma theta t plus delta t z. And that's all you're basically doing. You're saying, I know where we're currently at. I want to step in the direction of the score, and I want to add a little bit of noise. And the noisy part is because you're using a reverse SDE. you can actually get rid of the noise part if you use an ODE to reverse this process, which there are methods to do, but in this case they use an SDE. And this is the formulation they have. It's pretty intuitive, this solver method. And they do have some good visualizations to go along with it. But first, before I go on to those visualizations, I do want to say that instead of modeling the noise, like I said earlier, you're instead modeling the score. So you have the score matching objective as opposed to as opposed to direct noise matching. So this is score matching, which does so you can kind of see it does have this Z term in it. Sorry, you have this Z term in it. So it's modeling the score. It's basically modeling the score of the model, and you have this C term here because it's an SDE that you're modeling this based using an SDE. So you have this score matching objective here, which is different from the diffusion objective. It's different. You're modeling the score. You're not modeling the noise. You may be so that's the objective, and that's kind of the difference between your normal old diffusion model, which you've probably seen before, versus your score model. One models the noise directly, while one models the score. So those are the differences. And there's also multiple types of score models, which I want to quickly mention. So there's two types. There's actually three types that were introduced, but one is kind of in the middle of these two. So let me change my highlighter color. So you have two types of SDEs. You have variance exploding. So if we go to our original equation, variance exploding would keep, let me erase this is a lot. So variance exploding would say, okay, we keep our data constant. So that's basically what we have up here. We keep our data constant, and we progressively add more and more noise. So you have this image here, and you progressively add more and more noise to your image, but you don't change the original image at all. So in this case, the derivative of your image, the term in front of your image would be 0. So you just say alpha t is equal to 1, and sigma t is some term that increases with t, or maybe it's constant with t, but it's some term that increases the noise with respect to t. So as you go forward in your differential equation, you add more and more noise. So this goes from a normal distribution from, say, 0 to, say, sigma t, and it goes to some normal distribution, what do they say down here? Specifically sigma squared of 1, which is whatever you want this to be. But you can imagine, if you take the variance of this, it would start at some small value and maybe it goes to some massive value, thus the term variance exploding. Now, the second one is, you could probably guess, not variance exploding. And they call that variance preserving. Well, this was also mentioned in one of Song's paper, the variance exploding versus variance preserving. So, whereas the variance preserving satisfies alpha squared plus sigma squared equals 1 for t, where alpha is equal to 0, or alpha t goes to 0 as t goes to 1. So the idea behind this is, instead of keeping your image constant, instead your image, if we don't have any noise in it, then your image is slowly going to go from, say, cat, oh man, this just keeps on progressively getting worse, to, so you keep on removing this image to 0 times that image, which would just be a full black image. And if you add noise corresponding to the amount you remove from that image, so maybe you add noise kind of proportionally to the image you're removing, then you basically, maybe this is more stable, it has different properties to it, but it's another method of doing this, where instead of having this variance blow up in your data, you preserve it. And they say that P of 1 is equal to a normal distribution, a Gaussian with variance 0, or with mean 0 and variance 1. So you can kind of see the differences here, and they go with the variance exploding. I don't know why. I think they just pick one of them and go with that. Yeah, I think they just pick one and go with that as opposed to trying both of them, because you kind of have to come up with the sigma functions and make it work well. But yeah, they just choose variance exploding as opposed to variance preserving as well. So those are the two different types. And then there's also like a sub-variance preserve. I think it's sub-variance preserving, but whatever. Just multiple methods for going from your Gaussian prior to your data distribution. Multiple methods of doing that. Now, Song actually has this paper. So, yeah, Yang Song. Dr. Song has this paper where, and I think it has a really good visualization for how this works. So you basically have your data distribution here. So notice you have your high density regions here. And so this is what I was talking about earlier. Maybe this is your picture of your cat right here. And this is a picture of, say, a chair. And this is your initial distribution. So you have your image of your cat here. So be cat. Oh, wow, this just keeps getting worse. So you have your picture of your cat. And you slowly move along this noisy trajectory. So your noisy trajectory is your SDE. Notice how it still follows a path, because it still follows a path. It's just it's a lot more noisy because you model this as an SDE. And it follows a path to a Gaussian. So this would be your noisy image, your noisy Gaussian image. So this is how you would transform your initial image to your Gaussian, and this is one way of kind of visualizing that. So you can see it's your SD or your differential equation, or you can kind of move through this kind of gradient field and kind of move through it by modeling the SDE, and you eventually end up at your Gaussian at time step t. So then to sample from it and to reverse this process, you would train a model. So right here, this would be your model here, your score model, to reverse the process. And notice how it learns to reverse this to your original distribution. And notice how I really like this visualization, but notice how it goes to the high density regions. And maybe it starts at a low density region. So like this area would be low density, so it technically kind of starts over there. And you can kind of see that by the heat map. But it kind of moves along this trajectory to a high density region in the from the normal distribution to a high density region in your data distribution. And that's what the score allows you to do. It allows you to move along this trajectory into a high density region in your data distribution. And also notice that there's these white paths here. The white paths are the ODEs. So instead, if you instead model this as an ODE, there's a deterministic process that allows you to there's a deterministic process modeling the data distribution. And both of these are kind of used in practice. I think ODEs tend to be used more often, like whenever you look at the stable diffusion solvers. But I think either way, they both lead to an image in your data distribution. So that is how they model it. And yet another visualization, which is also kind of cool. So you have your image here. So in this case, it would be make this red. It would be a drawing that I would probably make. And they say you have this distribution here, which is maybe that would be, you have this distribution here, which kind of models this input, and you want to move to some part of your image distribution. So the noise basically allows you to do that because it kind of merges the two together, I suppose. It basically makes it a joint, I guess it makes it a distribution where you can move between the two easily. So you add some noise, and notice how you can kind of see the image still, which that is an important fact we'll get to later. And you can see it kind of moves along. So it starts here and it kind of moves towards the high density region in the image distribution, and it lands somewhere in a high region in your data distribution, and you get this nice looking image here. So they do this by using an SDE, and your model is basically the score it's used to solve this SDE. And they do bring up how they solve this SDE, and they just use the Euler method for SDEs. I'm not going to try to say the other name. And all it is you take your original image here and you add some noise to it. So your noise will be some time step t sub 0. And then you just reverse the process multiple times from n to 1. And n is your total denoising steps, which can be any number. And that's one of the nice things about the SDE is you can technically do this in one jump if you wanted to. It's probably not going to give you the best results, but you can do this in one jump. And it's basically how you discretize the SDE. So you obviously can't do this as a continuous process, but you can discretize it, and it allows you to choose how many steps you want to take in your process. Now, that's cool and all, but how do we relate this back to the original goal? So basically what they do is they train a model to go from this. They basically, well, actually, they don't even train a model. They just take an SDE model that goes from noise to image. And all they do is they take this, we'll just go up here. So they take this input image, they add some noise, so then it looks like some part in the diffusing process. And notice this isn't pure noise. There's still some image in it. It's like midway in your diffusing process, and then you unnoise it from there. And they don't even have to train an SDE model because there's already SDE models out there. You just take one off the shelf and use that. Now, there's a really important point they make, and that is this point which I mentioned at the beginning: realism versus faithfulness. So they define realism as so the image should appear realistic, and this is measured by humans or a neural network. And realistic is, say, this image here. This is a realistic image. A realistic image is one that just, I guess, it's in a very high density area of your data distribution. It's one that looks really good. It's a realistic image. Don't have to explain what that is. And yeah, realistic image. Now, on the other hand, a faithful image is the image should be similar to the guide, xg. And they model that using the L2 distance. And specifically, they model realism using KID. And KID is basically FID. It's just, it's slightly different. It's better for smaller data sets, I think. But it's basically FID. It's telling you how far is your distribution, your generative distribution, from whatever distribution you're trying to model. Say we're trying to model the bedroom data set. So it would say how close is the distribution you've generated to the actual bedroom distribution. So that's it. So you have realism versus faithfulness. It's a trade-off between the two. So if we look here, we can see that this is a really faithful image. So say I gave it this picture and it produces me the same picture. This is the most faithful the image can be because it's basically exactly the structure I wanted. So I give it this, and this is technically the most faithful image I can have because it's the most like what I gave it. Like I mentioned earlier, it's just use the L2 loss, and this has a 0 L2 loss because it's the exact same thing as my guide, as my original image. Now, on the other hand, this is very realistic. However, it's not very similar to what I originally gave it. If you can kind of see, this image here is very realistic. However, it is not very faithful because it's very different from the image from the guide I gave it. And they say that they want to have some sort of middle part, and that's where this T0 comes into play. And T0 is how far you go in your process. So 0 here is not adding any noise at all. while 1.0 here is adding 100% noise. And whenever you add 100% noise, you basically have an unsupervised process because there's no guide. If you add 100% noise, then you have no guide at all, and it'll be as realistic as possible. Notice they have that here. It's super realistic, but there's no guide, so it's not going to produce anything close to how I wanted to like the style of the image. So that's this example here, where I give it this, and if I add 100% Gaussian noise to it, so it becomes a pure Gaussian, and then I unnoise the process, or then I do the unnoising process, then it will produce me a really good looking image, but it's not going to be the style I wanted it. And in this case, if I add no Gaussian noise and then I do the reverse process, then there's nothing for it to remove, and it goes to the same image. So that's really faithful. So they say they want a sweet spot in the middle, and they say that there is such a sweet spot exists, and they find, they have a proof for it here, and they have an equation for it, which they say, and they have a proof in the appendix, and they say the above proposition suggests that for the image to be realistic with high probability, we must have a large enough t sub 0, where t sub 0 is where you are in the diffusing process, so that's where you start. That's how much noise you add to your guide. On the flip side, if t0 is too large, then the faithfulness of the guide deteriorates, and SDEdit will produce random realistic images, with the extreme case being unconditional image synthesis. So that's a trade-off that was mentioned up here. It's as you add more noise, it becomes more realistic but less faithful, but there's a sweet spot in between, which is this spot here. And specifically, they say a t sub 0, which is 0.3 or 0.6, works well. And all you do is add this noise, throw the SDE solver at it, and it does its thing and gives you your image. And that is their method. They basically have this SDE, which goes from noise to image, specifically from noise to image. Note that it's noise to image. It's not this to image. This is not your prior. A Gaussian is your prior, and you give it this, but you add noise to this in the process. So you don't model this guide. You model a Gaussian to whatever image distribution you want, and you use an SDE to do that. And then you go somewhere in the middle of the process with your guide to generate you an image. So now let's just go through some examples, because that's pretty much all the method is. It's just throwing an SDE at some point in the middle of the process, which, yeah, you can see. That's why they have here. This is somewhere in the middle. It's not complete noise, it's not complete image, so this is somewhere in the middle, and that's why it gives you a realistic output. So you can see here they give it's like user-created data, it's user-created guide, and you can see, it produces something that's pretty faithful and somewhat realistic. Also here, they do the same, and there's some other ones here. Those aren't particularly interesting. In the experiments, they say, yeah, we just beat everybody. They do much better than the GAN alternatives, and they just, it's not even close. So I'm not really going to look at the metrics themselves, more of the generations they do, because it's kind of cool to see. So, right, so this is image editing. So you can also do image editing. So you don't just do an intermediate point, but you can also do image editing where you do inpainting. So like this example here, you would maybe, not the highlighter. So maybe you want the pillows to be changed, and then it changes them to different pillows. There you go. And in this case, maybe you want this guy to have a beard. So gives him a beard. And the way you do this is, instead of saying, I'm going to throw noise at the whole image, you only throw noise at this part here, at the part that you mask. So this is inpainting, and you only throw noise at the part you mask. And whenever you're doing the diffusing process, you keep your entire image constant, except you keep the area that you mask. So it'd be this part here. You denoise that part, but the image still has context of the entire, like the model still sees the entire image. It just doesn't denoise the entire image. It may predict something to denoise the entire image, but you don't use that. You only use the predicted output for this part here, for the masked part. Same here. You would only denoise that part and so on. So that's how you do the inpainting, and you can see it does a pretty good job compared to the GAN alternatives, which was here, the GAN baseline. It's not even close to being good. Yeah, they just destroy them. And the final thing they do, which I mentioned earlier, is remove this. Is if you have this image here, you have your source image, and you say Photoshop some glasses on, then you can basically, well, it's over here. So you Photoshop some glasses on, and they have some other like blending techniques here, and they don't look too well. And this actually doesn't look terrible, surprisingly, because this was with that added here. But anyways, you just throw those on, kind of badly photoshopped on, and you can see it does a pretty good job here, and it looks pretty realistic, but it's also pretty faithful. So that's the trade-off you're looking for, and that's the trade-off, and it does a pretty good job with that. So you would give it this image here, you would add some noise, and then it would hopefully produce a very similar image with the changed part on there. So that is, and those are the three methods that they kind of show, and they still have more metrics, but this method is used in Stable Diffusion, and it's really good. So it's just something like just destroys all the other methods. It's really good. So yeah, that's pretty much it. They have a lot of proofs in the appendix and other solvers, but that is the method. Basically, just throwing an SDE at this task and just throwing an SDE at this task and kind of going in a middle area to achieve your result of being somewhere in the middle between super realistic and super faithful. So very interesting method, and it's probably why it's used everywhere.